All right, here we are. We are doing modern practical natural language processing. So the idea of this course is to make a set of videos that'll help you get started in NLP to do useful stuff right away. So we envision 4 videos. The first one would be this one, which is an overview and converting text to vectors. So you can find similar documents like, hey, I got this document and I have this huge set of documents. Let me find some documents that are like it, talk about the same stuff. Next video, we're looking at doing learning with vectors and classification. So you can classify documents and put them into buckets. Then after that, we're going to look at sequence generation. So the first 2 lectures are about converting documents to a vector representation and then doing useful stuff with a vector representation. The next lecture would be about sequence generation. So how can we translate a document or summarize it? And then the 4th lecture would be more symbolic, so extracting pieces of information from text. So like pulling out sentences that talk about companies or a mention of every street address in Garland, Texas. So some additional details. Speech to text also works pretty well these days. So if you have videos and you want to run NLP on it or audio, you can do that. And the code will be available at the GitHub repo Modern Practical NLP. So just a couple moments about me. I finished my PhD in computer science in 2010. Thesis work was about how could a robot wake up in the world and figure out what's going on. I currently work at D'Ambro, where we do AI for the Department of Defense. We also do some work in healthcare. And in a later video, I hope to show, not in this series, about how we can use graph neural networks to identify who's at risk for overdosing from opioids. I'm the author of The Curiosity Cycle, Preparing Your Child for the Ongoing Technological Explosion. So if you're home trying to teach your kids, maybe that could give you a little inspiration. I do some independent consulting work, and you can find me at Gmail and on Twitter. Okay, so just a few moments about the limits of natural language processing. So computers can't read. So reading requires mapping language to internal concepts in our brain, mapping what we read to these concepts, and then having these concepts that we map to come from the same general environment and use the same kind of representation as the writer. So when we pull the words off the page, we map them to our concepts. Those concepts presumably were in the brain of the writer, and then that's what reading is. And that's how we communicate with reading. And so computers don't have these concepts. They don't have the experience. They don't have the machinery to represent these concepts. So obviously they can't read. So for example, if you say, I pulled the wagon, computers don't know that wagons are used to transport things from one place to another. They don't know that pulling exerts this gentle tension on your arms and legs. And similarly, computers can't write. So writing requires taking concepts in your head and then mapping them onto words in such a way that the reader will map those words into similar concepts in their head. And of course, because they don't have these concepts and don't have this experience, computers can't write. So I talk a lot about this in a bunch of different blog posts. So you can, when you get to this Jupyter Notebook from the GitHub repo, if you're interested in more of things on this nature, you can look at these. Now, this course is not about the theory or fundamentals of intelligence. It's about doing practical things with AI, or actually more specifically practical things with natural language processing. So natural language processing is about how can computers read and write given that they can't read and write. So how can you take natural language and put it into a computationally amenable form so that we can do useful stuff? And one big thing that's happened in the last 10 years is we've gotten good at taking text and putting it into vectors. And so that would be most of the course. But we also do symbolic methods, which are practically useful, such as identifying businesses in text. So now the meat of the video. So here we are in video 1. We're going to generate vectors from text. And the way that this is important is because once you can convert something to a vector, you can then you can run a similarity score using Euclidean or cosine distance and say, oh, okay, I converted this document to a vector and I converted all these other documents to a vector. Now I can automatically find out which documents are similar, even though computers can't read. And this is kind of like roughly analogous to what's going on in computer vision. Is in computer vision, they take some image or a video and they convert it into a set of vectors, and then you can say, okay, in this image, is there a cat in there? Well, you can compare that with other videos with cats, or you can put a classifier on top of it. And so the computers can't really understand what they're seeing in images, but you can do some useful stuff, like classify faces and that sort of thing, or even figure out who's who. So, and this is still useful, and so this is kind of what we're doing in NLP. You can think of it in that way. So even though computers don't understand the world, they can still do useful things with video, and similarly, you can do useful things with text, and that's what we're going to cover. So today, we're going to look at PyTorch, which is like TensorFlow if you're familiar, and it does automatic differentiation, which means that when you do learning, it does the calculus to figure out how the parameter values should change so that your model better solves your problem. We're also going to use the Hugging Face transformer library that's built on top of PyTorch, or it uses PyTorch, and Spacey, which I've misspelled, S-P-A-C-Y. And it's the most common tool for NLP practitioners. So I'm assuming you've got some Python going. If you have Anaconda, you can create a new virtual environment if you'd like. And then you can install PyTorch with pip install torch vision. Then you can install Hugging Face, Hugging Face transformers, pip install transformers. So now let's do some actual code. So we're going to import a bunch of stuff, but importantly, we're going to import from transformers BERT model, BERT tokenizer, and BERT config. Now, BERT is a pre-trained transformer model. Transformer is kind of the successor to RNN, recurrent neural network models. And so instead of generating one token at a time, they have a whole bunch of tokens and use like a graph neural network and look around at the neighboring tokens to figure out what this token should be. So we're going to import our model. There are many models here. We're going to do the BERT base uncased. We're going to import a tokenizer. And this is important because a tokenizer converts the text into individual words or word pieces. And this is important that you use the tokenizer that was trained for the model, that was used to train the model, because if it converts like master of the universe into 3 tokens of the, well, that'd be 4. But there are certain words where it could go either way, like hugging face. It might break up hugging into hugging and face. So you want to make sure it breaks up the words in the same way. And we're going to import our pre-trained model. This is really big, so just be wary. It just means in practice that when you're running on a GPU, which we're not going to do GPUs here, but when you are running on a GPU, you can only fit a few examples in your batch at a time. And then you also want the parameters, so you know like how big your inputs can be and such. Okay, so we've imported our model. Hopefully that worked for you if you're following along at home. And now, first thing we want to do is we want to define a function that converts a text to tokens. Now, I mentioned that we have our tokenizer, which is going to do most of the work, of course. But we've created this nice little function, and I'm a big fan of type hints in Python because it makes it a little more, a little less Wild West. You can see what's actually going on when you look at this thing. It takes in text and like, oh, it's a string. That's very useful. It's a tokenizer. What kind of tokenizer? Okay, BERT tokenizer, config, a BERT config. And then it returns a list of strings. So we're going to just do the tokenizer, and we get our tokens. But we want to make sure it's not too long, so we'll just cut it off if it's too long. And we're going to add a special token at the beginning, which you can look at here if you're interested. And it basically is going to hold the vector representation of the whole sentence or text that we put in. So then we return tokens, and you can see I've already run that. That's nice. And so if we see here, if we have the text, I went to the store, then the tokens are, you run get tokens, and you print them out. You get this CLS, that's the first token I mentioned up here, and then you get I went to the store. You notice that it lowercases it. Not all models lowercase, but this one does. Okay, so great, we've got tokens. That's nice. Now we need to convert them to integer IDs, because in deep learning, each token or word piece maps to an integer ID, which somewhere deep in the system maps to a vector representation. And the way transformer models and sequence-to-sequence models work as well is that it takes these token vector representations and puts them together with word order and outputs a vector for the whole sequence. So what we have here is we have our tokenizer that we have, and we have convert tokens to IDs, and these are integers. So I notice here I just said, okay, this is going to be a list of integers. And up here, when I did all my imports, in someplace around here, from typing import list tuple, there you go. So, and then you print your token IDs, and here are your token IDs. These are going to be indices into a big table, but you don't have to worry about that. The BERT model takes care of that behind the scenes. But in order to use PyTorch and BERT, we're in a deep learning world, which means everything has to be converted into a tensor, which is in deep learning is just a word for a multidimensional array. Mathematicians have all kinds of, and physicists have their own fancy thing that actually means something more than that, but we don't have that here. So we have our token IDs tensor, is we just create a torch.tensor from that thing. And then if you print it out, you get, it's a size 7 and it's a tensor. So basically it's the same thing we had before, but now it's in tensor world, so Torch can understand it, PyTorch. Okay, so normally when you run these sort of things, you run a batch. So you run a bunch of sentences or paragraphs through at one time to make it fast on a GPU. But we're just going to run one at a time, but we need to make it a shape of size 1 by num tokens. If your batch size was 56, it would be 56 by num tokens. So that's just the old unsqueeze, and then we get our torch size of that. Okay, so now we can actually run our model. So what we do is we call the model, passing in our tokens. And we get two things, this last hidden state and the pooler output. The last hidden state is for each of the tokens you send in, the last hidden state of the transformer. And the transformer is like 12 layers deep. And the pooler output is the vector representation of that first token. And that's the one we want. And then we can say, we can print this thing out. And we can print out as type. So we see that, scrolling up here, we see that's a type tensor, and it's a big vector. So we have successfully created our vector. But now, of course, it's in this funky tensor thing, and we want it into regular old NumPy. So we just do vector detach NumPy, and then we make it one-dimensional again, and we print that out, and we basically get the same thing. But now we're in our happy NumPy world. NumPy ND array, which of course is the backbone of how you do anything in Python with numbers. So, okay, so let's take all that now and make it a nice function. So this function just does everything that we just did, but it does it all together, and it takes in a string and returns a NumPy array. Well, that's great. So this uses the transformer model. And so as I mentioned, the transformer model is a graph neural network with a lot of layers. One way it's trained is that for each token position, it looks around at the neighboring tokens to decide what it should be. So basically, they just mask out the token and say, given all the words around this word, what should this word be? And here's a great explanation of transformers. And BERT is a big pre-trained transformer model. So here's where you can find out more about that. Now, the transformer uses word order. So that means that the sentence, I went to the store, is going to be different than the sentence, store to I went, which seems like is as it should be. But you don't necessarily have to do that. You can just not use word order and just get a vector for each word and just take the average. So the vector for I went to the store would just be the average of the individual vectors for the words. And for that, let's look at Spacey. So to install Spacey, you do pip install -u Spacey. I said medium before, or I was thinking medium before and I typed this in, but let's change this to large. So here it is, the EN vectors web large. That way you get the nice big vectors from glove. Glove is one set of pre-trained vectors. And then, so we're going to import Spacey, and then you just load the model, assuming that you downloaded the model like this. And then you can just say tokens, NLP, dog, cat, banana, funky, AFSK. And then you can do for token and tokens, print token.token vector. So let's see here. So we've got dog as the first token, and here's its token vector. All right, so that seems to work. That's nice. So now we know how to get individual tokens, and so let's make a function. This is going to take in a text of string and return a NumPy array that gets the average vector for text. So we do tokens, NLP text, and then for token and tokens, we just create a list of vectors. Could have done that fancy list enumeration thing, but we didn't. Then all vex, we just make it a NumPy array. List comprehension, that's the term I'm looking for. We could have done that. And then we just make it an array, and then you can print out shape if you want. And then we just take the mean. So we're taking the mean of all the vectors for the words, and if you want, you could eliminate stop words. So like the word the, you could just say throw it out. But that's what our function does. And so what we're going to do now is we're going to run this on a set of my tweets that comes with the GitHub repo for this little course, and we'll see which one does better, the fancy method or the word-by-word method. So the fancy transformer method or the word-by-word method. So we're going to load the tweets. The tweets are here, and this is just regular old Python. All tweets, list of string for tweeting, just append them in there. And then we're going to generate the vectors. So this can actually take a little bit. I set up this thing so the first time you run it, it'll save them and generate them, but after that, it'll just load them from a pickle file. So here's your pickle file, and that's why we need all this path.home silliness. So no matter who you are, if you have a temp directory set there, you'll be all set at your home directory. And then I say, if this file exists, print we're loading them in. Otherwise, print we're loading them in and load them in. Otherwise, for tweet in all tweets, get your vector, append it and save it. Same for the average vector. Load it in if it's there. Otherwise, for tweeting all tweets, get average vector for tweet. And so when I ran this, I had already run it before, so I was just loading saved. Oh, and I did generate the I had the transformer vex, but not the average vex. That's why I generated the average vex. All right, so now we want to see, given a vector representation for a document, how can we find the document that's most similar? So if you look, it doesn't let me go over there. Anyway, so if you get the most similar, you get your text vector, and then you get a all right, what is this? We want to scroll over. I make that really hard in this life. Okay, so you get, and then you get your vector list of all the vectors, and find, given your vector and all your other vectors, get me the most similar, and you're actually returning how similar it is and the actual tweet that it came from. So, and this is done in the dumbest way possible, just brute force. I loop through the vectors, and you can get the distance either with Euclidean or cosine. The difference is the Euclidean distance takes the magnitude of the vectors into account, whereas the cosine vector just looks at the angles. The fancy people like the cosine. I found that it doesn't seem to make a ton of difference for me which one I use, but we'll use cosine to be fancy. And then, and if the distance is less than the smallest distance, right? So this is like a brute force method. Now you don't have to use brute force. In fact, you shouldn't if you're doing like major stuff. Going down here to get this thing is really annoying. Okay, so in reality, you want to use something like the face library from Facebook, and what that does is it does stuff behind the scenes, so you don't have to do a pairwise comparison between each pair of vectors, and so everything's really fast. So use that if you're using, if you had a lot of things to look at. All right. And then we just have get the most similar one for transformer, which calls our get most similar vector based on the transformer stuff, and get most similar tweet average, which calls the get average, which calls the get most similar vector based on the average stuff. All right. Now, maybe I should make this a little smaller. I wanted it big so you could see, but then if it runs off this page there. So we have 3 tweets. So if you look in the tweets, one of the first tweet I think is cats don't like to wrestle. So we want to make sure, of course, that it maps that to being similar to when it's mapped in the in all the dictionaries. Basically, that a tweet is similar to itself is what I mean to say, just as a dummy test. And then we're going to actually add some new tweets. Like this transformer vector approach doesn't work well on tweets because it was trained on other data. Seems like I'm giving away the answer here. And then the second tweet is I like to watch movies. And the third tweet is my children like to climb trees, drink water, and read about aardvarks. So for each of those tweets, those 4 tweets, we're going to look in and find the most similar tweets. So we're going to print out what it was originally, get the most for transformer, and then print it out for transformer, and then get it for the average, and print it out for the average, and then print. So now this isn't going to work very well, mainly because there aren't that many tweets. And so it's unlikely that I've written a tweet like any of these things before. So what we're looking at is the closest tweet. So here we are, the output when you run it. So the original is cats don't like to wrestle. And Transformer said, okay, with a distance of 0, cats don't like to wrestle. Well, that's reassuring. And then the average method did that as well. Okay, so we have no obvious bugs, is what that tells us. Or less likely to have obvious bugs. So that's nice. And then for the next one, this transformer vector approach doesn't work well on tweets because it was trained on other data. The tweet that Transformer found is most similar is children used to build either glue or snap-on models. Now Legos are so detailed that kids build with those instead. Okay, this has nothing to do with this. So bad job, Transformer. And this one is actually kind of good, given that there is no tweet in my database about this. It says, surprisingly, the search feature on Google Docs doesn't work very well. If only they had access to search experts. So this is me complaining about something not working very well. And this is the original tweet complaining about not working very well. Well, that's pretty good, I would say. Now, let's look at the other one. I like to watch movies was the tweet. Now, let's go into all of my tweets and find the closest tweet. And then Transformer says, I just watched 127 Hours with the special lady. Felt kind of bad sitting over my microwave popcorn and big glass of cold water. Okay, that's pretty good. And then the one for average is, I like a lot of kids' movies, but I just can't get into those Ice Age films. Well, and it's pretty good. I like to watch movies. I like movies. Now, this didn't mention anything about the Ice Age, but there is no tweet in there that just says I like to watch movies, so that's pretty good. Now, this last one's a pretty weird tweet. My children like to climb trees, drink water, and read about aardvarks. Now, this isn't an actual tweet. This is that one we just made up. And we're going to look in and see how well they did. Transformer says, it's funny how in a group the result of hoarding is more hoarding. That's not very good. But the average vector method did work pretty well. Amazing how kids practice actions. At age 2, my boy would go up the step, down the step, repeat. He loved it. It drove me nuts. So here we are talking about children doing stuff that kids like to do, and that's what this is about. So I'd say that worked pretty well. So tweets are a weird data set. They're short. They are kind of choppy, and they talk about weird stuff, especially my tweets. So you can't really blame Transformer. Transformer works well. It's trained on like books and things that are more coherent. And so the BERT trained model is going to work well if you use data other than tweets. Tweets are weird, and that's why the word average method works so well, is because these tweets are short and they're weird, and the order doesn't mean a whole lot, at least in terms of what the machine can do. You can fine train BERT in this unsupervised way, but it's a little more involved. I've given you a link here. So now, in conclusion, we have seen that we can convert natural language into vectors. And this is really powerful because now we can take natural language and do computation on it. In fact, we can do computation on it in a way that generalizes much better than the previous method, which was like TF-IDF, where you had to just look at the overlap in documents between the actual words used. What we see with the vector representation is it can know that movie and film are pretty much the same thing. So it can find that even if you don't have exact word overlap. And in the next video, we'll look at fine-tuning these vectors for classification. So we can put documents in the bucket. So we'll train it on our data and actually do some learning and use TensorBoard to plot our progress, and we'll have a lot of fun. Okay, thanks.